Okay, so today I would like to go over making some plot stuff. So I'm just gonna build on the same code we had the last time. But I think we talked about this a little bit, how the kind of plot that we want to make probably would look something like this, where we have our drug levels or whatever is over here on the y-axis. And we talked about this a little bit. Maybe we want to have, one line for the one group, right? And then one line for the other group. And then, of course, the data points themselves. Maybe there's some data points for like time 1, time whatever, time whatever, time whatever, time whatever. And then the data points for the other group. Where's my mouse? There it is. Like that, right? And maybe also this line has some like standard error associated with it. So maybe we also have like a shading bar around the line, right? Something like that, that shows what that is. And that's supposed to be a straight line. I'm just drawing with this pad right now, and so it looks like it's a hump, but that should just be a straight line. I could have used the line tool to do that, but I'm being lazy. So something like this I think would be good. And then maybe you add in a little legend, like this is group 2 and group 1, something like that, right? So this is the kind of graph that we want to make. So there are a few things that we need in this graph. We need to plot the data points, okay, as a function of, as a function of group and time point, right? So we need that. We need a line for each group, which is the fitted like line for each group. And maybe we need some standard error shading for each group. Oops. Oh, come on, I keep hitting these buttons over here. So it's important, it's a fine point to note that the standard error for these lines means the uncertainty around the fit. Meaning, like if I predicted that at time point 5, you're supposed to have 50% levels of drug or something like that, that's the error around that estimate. So the model has some error, like 50 plus or minus some fudge factor that we think is in the model for that estimate. That is not necessarily the same thing as the standard deviation of the data points themselves, right? That's just the data points as they are. Why is that? Well, because the model takes into account all of the data, right? All of the data, and it generates the best fit that there is. But it's possible that at like one time point right here, maybe the data are like all really close together. And at another time point right here, maybe the data are really far apart, right? That's possible. A linear regression model is going to predict the same sort of level of standard error that's like a straight line throughout most of the thing for the most part. Okay, so it's going to be a fit around this line. And so that's going to be the standard error of that line that's built across from like all of the data points in the whole model together. This is sort of what we mean when we say that there is this assumption in linear regression that every group or every time point or every whatever it is has the same amount of variance. That's an assumption of linear regression because it's going to be symmetrical the whole way down. You're not going to have a line that gets fitted like this and then have a standard error that like is like here, but then somewhere down here dips or something. That's not going to happen. It's going to be consistent. It's going to be one estimate of error or fudge factor for the whole line, right? So that's something to keep in mind. And that's why that's the way linear regression works. And so that's why if you do have data, like let's pretend for an example that you had data where suppose here's time point 1 and here's time point 2, and the data points are just all really close together for some reason. And then here's time point 3, they're all really close together. And then time point 4, they're all really far apart again. When we fit a line to this, it's going to fit its best fit line, and it's going to have a symmetrical standard error across the whole line. that it estimates. And that is a shortcoming of linear regression, is that it actually can't handle this kind of a situation where there's like better estimation at some time points than at other time points. It actually can't handle that at all. And this is, so if this is like a very prevalent thing in your data, linear regression might not be the best modeling tool. But this is what we say when we say that data violates the assumption of, well, it's an ugly word, but the word is, homoscedasticity. Homoscedasticity means that at every position, at every level on this thing where you have data, the data have similar variance. They have similar spread in the data. So this is an example of where that's not true at all, where there's different levels of spread in the data at different time points. You can still fit a line. Linear regression will return an answer to you, but it might not be as good of an answer as something else because these data don't really conform to that expectation. So that's something to keep in mind. Linear regression is just going to make one line, and it's going to assume an even error across the line. OK, cool. So let's go ahead and make some graphs. Where's my mouse? There it is. So cool. So I'm going to go ahead and just open up like the code that you had before and just like run the whole thing. If you want to run the whole thing that you had before, you can just hit Control A to select everything and hit the Run button, or hit Control Enter. And that just runs everything. So we just have everything in memory right now. So I'm going to go over all of the things that we have in memory, and right down here in my code is my plot. I'm going to put my plot section. I'm just going to go over everything that we have real quick. So move my little drawing pad away for a second. So a couple of things that we have. We have this table here, this data frame called D. That has all of our data in it. And if I do the view function on D and open it into a new tab over here, you can see this has the basic data, which is the drug levels and the genotypes and the time points. That's basically what this is. And this last column, if you recall, is the same thing as the genotype, and it looks like the genotype, but underlyingly, it's actually a number. It's actually a factor, so you either get a 1 if it's this, and a 2 if it's that, and then the linear regression model interprets that as like a 0 or a 1, basically. So like this looks the same as this, but this is actually a number that simply has a label on it. So it's either 1 or 2. So that means we can split it up into two groups based on that. And we also have the natural x-axis is, of course, these time points, right? That's going to be the x-axis is like each of the time points. And then the data here. So what we need to do in order to plot the data points is we need to have a table. We need to add a couple columns to this table. So the first column we need to add to the table. Whoops. So we have our time points. And we have our drug level, or whatever it is. And we have our genotype as a factor. That other column is in there. I'm not worried about it. So maybe you have time point 1, time point 2, so on and so forth. And you have your drug levels here, and you have your genotype as a factor. Cool. Great. There are a couple things I want to add. The first thing I might want to add is I might want to have a color for my data points. Like I might want to make all of the data points from one group one color, and all of the data points for the other group another color. So I'm going to add a color column that's going to maybe select, I could do blue and red, we could do anything you want, selects a color for one group and a color for the other group. Because that way, what R is going to do is it's going to plot this, and based upon this information, choose a color, right? Cool. Great. So if we have a color column, then that makes that easy. And then we actually might want, now if I plot this the way it is, we have like 50 data points or something from each group. So if I do that, let's say this is time point 1, it's going to put all of these data points in like one line, and you're not going to be able to like see them clearly away from each other, right? So what I'm going to do is add a little bit of jitter as well. That makes it nice. That's going to like spread the data points out centered around the correct time point that it is, but just kind of make them so they look more like a little cloud. so you can kind of see them apart from one another. Because if you don't do that, like two data points that are very similar in value will be like literally right on top of each other, and it'll be hard to see. So I'm going to add a little bit of random jitter just to like move them left and right just by a little bit, just so that you can do that. And then we'll do that to plot all the data points. So let's go ahead and do that real quick, because those two things are very, very easy to do. And you'll see how we feed them into the plot function. So into D, I need to add that color column. So I'm going to say D, let's call it COL for color, equals blue. That's going to make every single data point in that blue. So you can see this over here. And blue has to be in double quotes. So it's going to be blue all the way across, like all the way down. Okay. And then I'm going to say this. We have to parse this line, but hopefully it'll make sense to you. We're going to add a logical test to this, and you may have done a little bit of logical indexing before. What were you working at Python or something? Yeah. Okay, there's maybe some logical indexing. This may look familiar to you. I'm going to take D geno equals G, I think it's 2, 2, right? Equals red. So what is this going to do? Every place in this vector, remember D $col, that's this whole vector of values here. Wherever this other vector happens to equal this value, we're going to set that to red. Does that syntax make sense to you?
A little bit.
Okay, let me do it in a couple steps, and that'll maybe help with that. So the first step is I'm going to say k equals, okay, let's do this first before we do that. D $geno, double equal sign is a logical test, so it's going to either return true or false whether or not it equals that. Okay? So let's inspect k real quick. So if you look at k, you can see that for each position it's either false or true. So there are all of the falses up top and then all the trues down below. Does it look like that for you?
No.
That's because okay. Did you equal it? Did you like set it? Did you run it?
Oh, wait.
Did you actually run this line of code? Okay, you ran it. Now type k.
Oh, you have to run it first. Okay.
Yeah, you have to run it first, because otherwise there is no k. K doesn't exist.
Okay.
Yeah, so object k does not mean it's not in there. Yeah, there you go.
Oh,
so
okay.
yeah, so now you should have some falses and some trues, right?
Yeah.
So that's just running a logical test, right, wherever that is, right? Okay, cool. So now, if I say true, let's say true vowels, let's call it that, equals which k, that's going to find all of the values of k which are true, right, and give me the ID numbers. Okay? You see that? So if you see this, then true values returns all of the numbers in that vector where k equals true. Do you see? Does that work for you?
What do I type in the console?
This right here. The which function hunts the true values. So this is what you want to type right here. I mean, I just said true values. You could call it ABC, anything you want. Okay? So do you see how, so then do that and make sure you can return that.
Yeah.
Okay, so now these are all the positions in that vector where it equaled true, right? Great. So now it's just an indexing problem. I can say D call true vals, right? That's just going to, right, remember, what does this do? D call 1, that would just pull the first value of the colors, right? Which is blue, right? If you can see that from the console. By the way, if you don't know this by now, Control-Enter from the keyboard runs any line of code in your console, yeah. So I just highlighted this just to show you what it does. So if you do 1, that's that. Now suppose we do 1 through 3, right? This should be similar to Python, right? That's blue, 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 right? Additionally, I can put any vector in here and say 1, 4, 5, 10, 100, 250, right? And that will return just whatever those values are, but they're just all blue right now, right? So now I'm going to use true vals, right? Because that's just going to pull those specific numbers, those specific entries. Does that make sense? Okay, cool. So now if I set these equal to red, it's going to replace the values in those numbers to the word red. Does that make sense? Okay, cool. So I'm going to do this. And now if you look at that column, you'll see, whoopsies, I made a typo. This is just a S. Okay, so now you'll see that that first set of entries should be blue, but now all the ones at the end, if you scroll all the way down, at some point, let's use this thing over here. All these will say red, right? Because it said basically change number 553 to red, change number 554 to red, change number 555 to red, and all of that. Okay, does that work for you?
There's like an error in the view. Can I find function view?
It's capital V.
Oh, capital.
Yeah. There you go. Yeah.
Okay.
Yeah, and there's nothing in call. Why is that? When you go back to your code real quick, not them all being untitled, you gotta save.
I don't know how to title them.
You save it. Just hit the save button.
Oh.
Rerun dcall equals blue. Rerun all of this stuff. Great. So now go back to the D. It automatically updates. There you go. So the whole thing's blue. Okay, so let's go through the steps real quick. So go back to your main script wherever you're doing stuff. Okay, now start by saying dcall blue. Just run that one line. Cool. Now, just from the console down here, just type dcall with the $sign. Yeah, there you go. Everything's blue. The whole thing's blue, right? All of it is. Okay. Now start from K and run those few lines. There you go. And now hit dcall again. Just take a look at it. All the end ones are red, but if you scroll up enough, you'll see the other ones are blue. Okay? So it's using those values. Doing this step down here does all of this in one line of code.
Oh.
Right? Because it basically says wherever this vector equals this value, whatever those numbers happen to be, change the value of this to that. Does that make sense?
Yeah.
Yeah, sweet. That's called logical indexing, and it's a super easy way of changing things around real quick. So in this case, now, why did I do it the way that I did? I'm going to delete these lines. I could have done it this way instead. I'm going to show you the way I did it instead. I could have initialized this as just anything, just like something empty, right? And then I could have said dcall dgeno equals g11 equals blue, and dcall dgeno equals g22 equals red. But as you can see, I could have just made everything blue. I only have two groups. I could have made everything blue from the start. Those are already done, and then just change the ones I wanted to red. So it's the difference between doing things in 3 lines versus doing things in 2 lines, right? So that's one way to do it. There are lots of different ways to do it. There are actually some more elegant ways to do it, but I think initially this is the best way to do it. So now, if you look at D, now we have this column here, and we have the color specified, okay? So if we want, I'm going to go ahead and create a plot, and then we're going to edit it a little bit more because this is not going to look the way that I really want it to look yet. But I'm going to go, and we're also one more column. D, we'll call it Y, equals the log 10. Because remember, we fitted this on the log transform of the data. So we're going to do dy equals the log 10 of D LPAM. That's the blood levels of that drug. Because that's what we're really going to plot on the y-axis, is that logarithmic value. Cool. So now, if I wanted to make a plot, I'm going to just do it just like this. Did you run that since we're just one-on-one today?
Yeah.
Okay, cool. So you got Y in there, and you got the color, and you got time. All that's set. Yeah?
Oh, wait, it says, I might have been typo. I expected the right concept.
Why did you put the extra D with that? All that stuff. There's not a function there. Yeah. There you go. Now run it. Oh, that's a 1, not an L. See how there's a 1? That's an L. Yeah, there you go.
Oh, okay.
Okay, cool. Great. Cool. LPAM stands for lorazepam, which is the name of the drug. Okay, cool. So now that you have that, now we can make the plot. So now we're going to make the plot. So to do the plot, we're going to use the same syntax we use for the model building. So we're going to do plot, and we're going to say y as a function of time. That's all we're going to do. And it's going to know to take the data values. But we're going to say the following. We're going to say that the data come from D, which we already know that, And also, we're going to add a new parameter called the color, COL equals D $ col, because it's going to take the color for each data point from that vector that's in the big table. And it should look something like that. Okay? You ready to see the graph?
Yeah.
Okay, great. Now we're going to change some more things, because I hate this like open circle thing. I'm going to say PCH equals 19. That's my favorite plot character. I use that one a lot. So you'll see what that looks like. That's like this little filled diamond thing.
Yeah.
Okay, cool. So now you should see this, and this is basically what you should see on screen. So you can see already that the red dots have like a little bit more maintenance of the drug level over time, and the blue dots are starting to decay a little bit more, whatever. Cool. So that's how you do that. So we were going to put the 2 lines on top of this. So this isn't as nice of a thing that I was plotting on the other when I was just drawing it, because obviously whatever I was drawing, there was much more separation between the groups. This doesn't have as much, but these are real data in that paper, or the simulation of those real data. That's cool. There are a couple other things that we're going to change, though. The next thing I want to add is I want to add a little bit of jitter to the left and right, because you see what I mean, right? All the data points are like right on top of each other. So it would be nice if you just like move them just a smidge, just a little bit left and right. Keep them centered around the whatever x-axis value they're supposed to be, but just like scooch them. You'll be able to tell, right? It's not like we have data all the way in between whatever how many hours this is and this one, right? So you could just move them a little bit this way and a little bit this way, and we'd understand that it was whatever this time point is, right? Okay, cool. So we're going to do that. So we're going to say D $, let's call it jitter. That's usually what that's called. And we're going to add a little bit of jitter to this. Now, my question for you is, how do you think we'd accomplish this? Guess. What do I have to add? What am I adding into the system by doing this? Think about it mathematically. What do I have to add to the x value to get this to happen?
Plus or minus.
Very good. Plus or minus what?
Any number.
Any number. So let's keep going from there. If we're talking any number in computer science, what are we doing? We're picking
Yeah, I don't know.
a random number, right? We're picking random numbers, right? So you need to pick random numbers. We're going to have have you ever like done a random number generator?
Import random, that's all.
Okay, but you've never like actually said to a computer, give me just a bunch of random numbers?
I think I have. Yeah.
Okay, cool. So that's basically what we're doing. We're just asking the computer to give you random numbers. Now, here's the question I have for you. If I just tell the console, okay, I want you to add any random number you want to this, what kind of problem might that create? So we have a data point that's centered at 25 hours. What if the random number that it picks is add 100 to that? That might be a little bit insane, right? That's going to push the point off to like a really far distance, right? So we need to be able to restrict the random number. So if I had this data point right here, I obviously don't want to spread it out such that it goes all the way over here, right? That would be crazy. So when I add, so let's say this is, I think this is probably like 22 hours, something like that. What do you think the maximum amount of distance I could add to that would be?
If it's at 22, then 8 plus 8 or minus 2. So
Plus
it's
8.
10, right?
Well, think about it this way. If I add 8, that's going to put that data point all the way over here. Do you really want to move it that far?
Oh,
Okay.
No.
Okay, so how far do you think you want to move it?
Just 1 or 2.
Okay, so maybe just 1 or 2, right? Maybe even less than that, maybe even like a fraction, right? Because if you put it at 22.5, it would still be close to 22, but it would be spread just by like a little bit, right? Or if you moved it to 21.5, that might work too, right? Cool. So we're going to add random numbers that are limited between plus or minus a small amount. So that suppose I tell you, computer, I want you to give me numbers between negative 0.5 and positive 0.5. So anything you want between that, right? And then add that to t. Because now if you have a vector, suppose you had a vector, I'm just going to do this from the console real quick. You don't have to copy along, just watch on the screen. Suppose I had a vector that was like c equals 0, negative 0.5, negative 0.3, positive, or 0, 0.1, 0.3, 0.5, right? If I added that to 22, all those data points would move right around 22 by like a little bit, right? But that's as long as I restrict it. If I didn't restrict it, if I allowed these to be anything, this would get insane, right? This would be like 5. you know, like negative 1,000, like negative 2. Now this, if we plot this, that's going to be insane. All the data points will be all over the place. That will not be a good decision. So we're going to keep our jitter restricted to a certain amount, right? And that's a parameter, and we might want to like think about that and play with that parameter a little bit. But the way that we do that is by doing the following. We're going to use random numbers have to come from a distribution. You can have like normally distributed random numbers, right? You could have random numbers from any distribution. We're going to use something called the uniform distribution. And so in R, whenever you pick random numbers, you take the name of the distribution, you just add the letter R in front of it. So RUNIF picks uniform random numbers. What does uniform distribution mean? That means every single number you pick from whatever you say, like pick from -1 to 1, every single number in there has equal probability of being chosen, right? So let's think about this. Let me just draw this. Actually, this is a worthwhile opportunity to talk about random number generators a little bit. Suppose you said, I want random normally distributed numbers. What does that mean? I want random numbers that are normally distributed that have an average value, I can't draw, an average value of something, let's say 0, plus a standard deviation of, I don't know, 0.5. One standard deviation is like about there maybe, 0.5, and then this is minus 0.5. But what do you see? All of the values in here have higher probability of occurring, but not equal. Like some of these values at this level will be less probable than these levels, right? And these values out here will be really unlikely, right? A uniform distribution is basically one that says if we're at minus 0.5 and 0.5, the probability of any value in that is like all the same. So the random number generator will just pick any random value, but it can truly choose any one that it wants. And there's no additional probability that one of them might be more likely than another one, right? So that's why I use that function, but you could use a different function if you wanted to. So the random number, the RUNIF function takes 3 parameters, okay? N, min, and max. So n, min, and max. So we have to set all 3 of those. So n is the number of random numbers I need. So that's just the number of things that are in D, right? So you can use the nRow function to get that. That's just the number of rows that are in D. I need 1 for every row, right? Min, let's say we did -0.5. Let's see what that looks like, and we'll tweak it. And the max is positive 0.5. Okay? So if I run that, now if you look at D, you'll see that there's this jitter column, and you can see that the jitter column should have only numbers that are restricted to live between -0.5 and 0.5. Does that look like that for you?
Can you go back to the code again?
Yeah, for sure. So there are 3 parameters. There is n, which is the number of things that you need it to give you, the minimum value that they can be, and the maximum value they can be. Yeah, that's right.
But it says error.
No, it's nRow, not row.
Oh, nRow.
Yeah. nRow means number of rows. It means count the number of rows. I could literally look at D and see it says 684. I could put 684. But you want this code to be generalizable to like whatever D is, right? So, okay, cool. So now it has random numbers. Now, if you redo the plot, okay, I'm going to say replot y as a function of t, but we're going to add the jitter to it, right? So what I'm going to do is I'm going to create a new variable, and we're going to call that t2, which is just t plus jitter. I think, let me see what happens. Don't do this yet. I want to see what happens if I do this just in here like that. Oh yeah, no, that doesn't work. Okay, never mind. Okay, so make a new column here, which is, whoops, D. We're going to add the jitter column to the t column together to get a t2 column, and that's what we're actually going to plot. Oops. So t2 is going to be the t with the added randomness to it. Okay, so now if you plot y as a function of t2, forget this part that I wrote here, I didn't think that was going to work. Y is a function of t2 now instead of t, it should have scattered everything by 0.5. So let's see what that looks like. Now it should look something like this. You can see what my graph looks like?
Yeah.
Okay, does that work for you? Sweet. So that's how you do that. So 0.5 works pretty decently here. That's like a decent looking cloud. You can kind of see all the data points. It gets a little bit scrunched towards the end part here. You can see that. Like it gets a little scrunched because there are like a lot of things that kind of pressed up together. But for the most part, this isn't so terrible. I'm going to actually change this to negative 2.5, or excuse me, negative 0.25, just because I think it might, especially at that lower end, it might look a little bit better. Yeah, it's a little bit nicer. It like keeps it a little bit more close together. Something like that.
Yeah.
Okay? So that like at this end of the graph, it doesn't, like these two time points don't get all scrunched together. So it's a little bit better, I think. Cool. Great. So that's that. So now we need to add some more things to this plot. And one thing that you'll notice, first of all, if you look at the x-axis and the y-axis, one thing you'll notice about the x-axis is R has decided, okay, it looks like your data go from about 0 to about 50 hours, and we're just going to split that up into 10, 20, 30, 40, and 50, right? That's reasonable. But you might actually want the x-axis to be the literal time points that are in your data, because it's kind of hard to tell, like, is this 22, is this 25, what is it? Obviously, there are no data points between 20 and 50, so it kind of doesn't make sense to have the 30 and the 40 here. It would be kind of better to have tick marks just at each time point that you like literally have so that the reader can look at it and say, okay, that's the 22-hour point, that's the 48-hour point, like whatever that is, okay? So what I'm going to do real quick is we're going to redraw that axis with custom tick marks instead. Okay, so this is a little bit more customization. So I'm going to add one more thing to this plot function. I'm going to say x_axt. That's a parameter that sets the axis. Okay, and we're going to say that that is equal to n in double quotes. What that means is it's not going to plot an x-axis at all. So when I run that, you will see that there is no more x-axis. That should look like that for you too.
Yeah.
Sweet. So now we're going to manually add the x-axis only at the places that we actually want it. Okay? So to do that, I'm going to say axis. The axis function takes a few parameters. The first parameter that you have to give it is the side. So the side, you can see that with this little pop-up that happens when you type the function. This lower thing here, this is considered side number 1. Where the y-axis is considered side number 2. The top part is considered side number 3, and this part is considered side number 4. So you could put an axis at any one of those locations. So I'm going to say axis at side 1, and then we have two parameters. We put the at equals, and then we're going to put in a vector, which is the specific places we want. We have a data table. We have a column of numbers that has all the time points, right? I don't want to feed that in because there's like a million different ones and a million different 48s and 22s. What's a function you think I could use to like simplify that down to just where the actual values are? Think about it. You must have done this in Python, but it's okay. I'll give you a pass because you're a high school student. You must have. I'm going to let you think on it, because if I have a vector, right now inside of D, we have this vector that, oh god, there it is. We have this vector that's 1, 1, 1, 1, 1, 1, 1, 1, a million of them, and then maybe 10, 10, 10, 10, 10, 10. I just want to get it down to be 1, 10, 22, 48, whatever it is, right? What's a function I could do just from your Python knowledge or other knowledge that takes a big thing with repeated numbers in it and just extracts what the specific numbers that there are, the limited list of what there are in it? I'm trying to say this without using the name of the function.
Yeah, I don't know. I don't think it's in Python.
What kind of values am I looking for? They're absolutely exist in Python, no question.
Okay, let me be real with you. My Python teacher wasn't the best.
Not drag your Python teacher.
No, it's because he didn't ever teach. He made
Cool.
us do like on a website module,
Oh, okay, fair enough.
and that was like it.
What you want to do, well, think about it mathematically. You're looking for the unique values, right? So surprise, surprise, there's just a unique function.
Yeah, that was the
Really? Wow. Pretty much every language has a unique function. So what a unique function does is, so let's go here, go to the console real quick, and just type. By the way, if your console gets like there's like too much stuff in it, and you're like, I just want to clear my head. If you hit Control L from your keyboard, that just clears the console out. Okay. So now just type $T. I just want you to see, not T2, just T. You see how there's like a bunch of repeated elements, right? Okay, cool. If you do unique of $T, like that, you'll just see the unique elements.
Yeah.
Okay, cool. So now we can say in our code up here, we want to draw the axis just at the unique elements. We're going to say $, unique $T. That's where we want to put the axis, just at those values. So we're just going to take that whole function and just stick it into the at label, or in the at parameter, rather. So if I do that, there they are.
Yeah.
Okay? So now you just have them at the specific place where they are. Now, one thing you'll notice is that you see how the fonts, like R decides, well, I'm not going to be able to write 1.5 and 2 here because it's going to overlap with the other labels and it's going to be too big. You can actually change the size of the font too. So I'm going to add another parameter. And when you add this new parameter, I'm going to have you have to rerun the 2 lines because it has to, otherwise it's going to draw over what we just drew, and like that's going to look messy. Right, so I'm going to add this parameter called cex.axis. I forget what cex stands for, but it's like the size of the font size. And it's in a percent. So 1.0 means whatever the default is. 2 would be a twice larger size, and like 0.5 would be a half, like 50% size font on the font size. So I'm going to make it say 0.5. If I rerun these 2 lines, now you can see those numbers are a lot smaller. And you can find a happy medium in between. Maybe 0.7. It might not be perfect. Oops, I gotta rerun the lines. There we go. Something like that might be good.
Yes.
Okay, so you can mess with that and like find a size that's good. No matter what you do, R is still gonna be unhappy when you have like these ticks that are like scrunched really close together. If you really want those to show up, you might have to just edit the image later in software that you like and like put those in manually. That's usually what I do for that. But you can play around with it until you find an option that you like. There are also lots of, by the way, there are lots of additional packages you can install that make fancier looking plots and have more options. One common one is called ggplot. A lot of people use that to do all their plotting. I actually do all of my plotting with the just built-in normal regular R functions for that. I don't have any.
This is what you do.
What's up?
So this is like what you do in the lab.
Huh? Yeah. Yeah, so like when I make a plot, I just use R to do that, yeah. Okay. So now, rather than using some other function. So now I'm going to do the same thing. That y-axis, you see that y-axis? I don't actually like those numbers. I like them like sort of rotated the other way, right? So I'm going to go ahead and do that. So I want you to go back to the plot function. We're going to add another option. We're going to manually draw that y-axis too. So we're going to say y-axt equals no, or n for, it's not going to draw it, okay? So now there won't be an x-axis or a y-axis. We're going to redraw that x-axis. Now we're going to add the y-axis. So say axis, now this is side number 2 is where the y-axis goes. Where we draw it, that's a good question. I'm going to draw it at the following places. We're going to put it at, use this, there's this function called, okay, so before we get crazy, let me go to the console and explain some things. The y-axis before, I think, went from like -2 to +2 or something like that. So you could type it manually, or you can use this function called the seek function, and that starts at, let's say, from -2 to +2 by 0.5, for example. If I do that, it's going to make this vector, right? So that's convenient. I could do that. I could do it by 1, and that'll make this vector. Okay, so I'm going to put this, I'll like the 0.5 version, put this, whoops, my bad. Put this in my at right here. You can see how you can nest these functions inside the plot parameters to like get other things that you want. So I'm going to put that right in there. And if I do that, then I'll have this. And I'm going to play with that axis too. Okay, that makes those smaller. And finally, what I'm going to do is I want to turn them all around. And that uses this other parameter. If you like look up all the parameters that there are like a million of them, you can just Google it. But like, it's the LAS parameter that has numbers that mean like how to rotate the things around the labels. So the default is the way it looks. In other words, the default is parallel to the axis that it is. If you want it to be perpendicular, i.e. rotate them 90 degrees, just like, then you use LAS equals 2. So that will make them look like that.
I'm really still typing.
Oh, you're fine. Do your thing. I'll come around. We got one-on-one today, so it's very easy. We got all the time in the world. I think you got everything. Yeah. Unexpected comma. You got an extra. Oh, it's because you accidentally closed. You have an extra parentheses right there. Now you should be good. There you go.
Oh, okay.
Yeah. Okay. Cool. So these are all the things that you need to mess with. So just to review, this parameter sets the relative font size to whatever the default is. And this parameter sets the relative rotation. So one is whatever, if the axis is going up and down, then that text label is going to be rotated to like match the direction of that axis. And then if you need to rotate it a different direction, you can adjust that parameter accordingly. Cool, fantastic. So great. So let's do some other things while we're at it. There's some other things you can specify. Right now, R is deciding that the limits. So if you go down here, let's look real quick. I want you to use, we're going to learn a lot of random little functions today, but it's okay if you don't memorize them all. I want to know, if I want to really draw that y-axis to look nice and like go from wherever the top of the data are to the bottom, I need to know what the range of the data are, right? Or the range of the data is. So if you use the range, whoops, not all caps, range dy, right? You can see it goes from negative 2.3 to positive 2.45. Okay, cool. So I'm going to change this a little bit. I'm going to say that I want my y-axis to go from negative 3 to positive 3, because that way it really has a tick mark for like everything, right? So we'll do it that way. That sort of adds those extra tick marks right to the top and bottom. So that's nice. And I'm wondering, oh yeah. And then inside the plotter, I'm going to add some more things. You ready for it? I'm going to add a y-lim, because you see how if you look at this right now, you can see how it stops at 2.5 on the top and the bottom, even though I told it to go from negative 3 to 3. And the reason for that is R has decided that, okay, we got negative 2.3, 2.45. I'm going to set the limits to 2.5, right? But I can set the limits to be anything I want. And I'm going to set the limits using this y-lim function. So I'm going to say y-lim is a vector that is, let's say, negative 3 to positive 3. And if I do this, then I get those extra things, and it looks like that. Okay, cool. So the y-lim is also an x-lim. We don't really need to set the x-lim, because I think we got all the data points, so we're cool. But if you wanted to specify that you wanted the x-limit to be further out or something, right? You can go in here and you can directly specify you want the x limit to go from a certain position to a certain position. Great. Additionally, we're going to add more things. I'm going to go ahead and hit the Enter key right before this last parentheses just to give myself some more room so I can read what I'm doing. I'm going to add another comma, but then go to the next line. I'm going to add the XLAB, stands for the label. Okay? I'm going to say that is time in hours. And then I'm going to say YLAB, that's the Y label, and we'll put that, and we'll say log drug level, because it's the log transform of the drug level, log 10 drug level, right? Okay. So now if I run all those things, now you see those labels have now been changed. Okay. So these are all just little things to customize to add additional labels and stuff to the axis that weren't there before. And what's nice about this is that if you make graphs for your own data, like for stuff you do this summer or anything else, is you can just kind of take this code and modify it a little bit and kind of get the labels and things that you want. So this is kind of a little template. Your data won't be exactly like this, but I think by learning this stuff, you kind of can figure out, okay, how do I want to change things to suit what I need to do? Cool, great. So now we got all of that. What else do I want to add to this graph? I think that's probably good.
Can you add a title to it?
Yes, absolutely. So the title, you can type main, okay? So main is the main title. That's going to go at the very top, like up here. So I'm going to put the main title and be lorazepam level over time. Let's just call it that. Okay. Whoops, and then run these two again. Cool. Sure, whatever, something like that. Okay, so you can do that. And there's another thing you can add as well. There is a sub, which is the subtitle, but that actually ends up going down here below the x-axis label. Why do I put that? I'm going to go ahead and put sub is genotype by time interaction, because that's what we're plotting here. Whatever, something like that. You imagine you put anything else and you'll see where that appears. It'll appear right below that time axis. Now you can actually, I'm not going to go into it today, but there is another function. There's the general purpose function called the text function, and that labels you based on coordinates to put text anywhere on this graph that you want. So you could say, I want to take some text and I want to put it right here, and you have to play with what the x and y values are for that to like figure out, like, okay, I need to go at about 24 and whatever that position is, and then I can put any text that I want there. Okay, so you can use that to directly put text anywhere on this graph that you want, in addition to the like built-in ones. Okay, so you can really modify this a lot, but that you have to start modifying things based upon the coordinate, which involves a lot of like playing around with it. Like, okay, I'm going to scooch it by this many x units to like get it to be right here, and at some point that might not be worth it. But you can always add, you can always open it up, put it in, paste it in PowerPoint, and like just drag that on later yourself, right? You can always do that on your own. You don't necessarily need to use R to hard code it in, but some of those things are nice. Great. So that is making the basic plot. Do you have any questions about this part of it before we continue? Okay, cool. Great. So we learned a bunch of things and we made the basic plot. Now we're going to add lines on top of the plot. Okay? So we're going to add lines on top of the plot. So to do that, we're going to use the lines function. Okay? But before we do that, let's think about this. To get the fitted line for this, we don't actually want all these data points, right? We actually want a single point for each group at each specific time point and then draw a line connecting them, right? That's what we want. And we don't need the dot for the point. We just need the line connecting those points together, right? So we don't actually want all of the data that's in D. We actually want the predicted values just for like the specific time points that we want. And we need those predicted values for each group too, right? So we're going to make a new data frame, and we're going to call that line data. And the line data table is going to be a small table, and it's only going to include the specific time points we want and the two groups, and then we'll use the model to calculate what the y values are supposed to be for those points. Because then we could go back in and just plot time versus those points, and it'll just draw the line, right? So I'm going to say line data equals, we're going to use a special function, and the special function is called the expand.grid function. And I'll show you exactly what this does in a second. It makes more sense for us to just do it, and then you'll see what the answer is. Okay? We're going to say t equals unique d $t. We want to take the values for time from that unique vector of just whatever it was, 1, 1.5, 2, whatever. And then we're going to say geno equals levels d $geno. So remember, geno is a factor. So if I run the levels function, you can see that's g11, g22, right? It's pulling the unique values for that function. If I do this, watch what happens. This is like easier to explain just by doing it. Look at what line data has. It is a small little table that just has the time points, like each time point, and the value of the group. So this is exactly what we need to make the lines, right? Because we need one line for each group at just these points, and we just need to add in the y values, right? Does that make sense?
Yeah.
Okay, cool. Did this work for you?
Wait, can you go back to code? I missed like one tiny part.
Yeah, you're good. You're good. You're good. So basically, you need one column for like each variable, and then you just need whatever the unique values of that variable are. Okay. So let me.
Run it, but I didn't get the line. Oh, I didn't get the line.
Yeah, you need to save it as a variable. Let's see. It's actually nice to do one-on-one because I feel like I can just go up and directly see what you're
Yeah,
doing.
I got it.
Sweet, great. So don't change what you've done in there. I'm just going to demonstrate up here what the expand grid.function does. Basically, it's making all the possible combinations of the three variables that you give it and making one big table out of those, right? So if I said Gino equals, let's just give it some vector, and that vector is A, B, C, D, I think you can expect what's going to happen is it's going to have the time points at each of those things. So it's going to have 1 through 48 for A, and 1 through 48 for B, and 1 through 48 for C, and 1 through 48 for D. Okay, so it's a convenient function for quickly generating a table that is the all the possible combinations. Like if I have 1, I need 1 for this group, this group, this group, and this group, right? And if I added another variable, it would make all the other unique combinations of that. So it's a unique way to get this sort of like example table of like all the possible values for the whole system. Cool. Okay, great. So now we need to add in the y values for these, right? So where are we going to get those? Well, we have to use the model that we have to predict them. So hopefully you have, make sure in your environment that you have MDL in the workspace from what we ran from before.
Yeah.
Yeah, okay, great. Cool. So now we're going to say line data $y, okay, equals predict. Okay, predict takes a couple things. We're going to give it the model, right? So give it the model, and now we're going to tell it where new data is coming from. New data equals line data. So we're giving it this table that we have, and we want it to predict the y values. And now you can see, whoops, that if you did that, it just does it. So there they are. Those are the predicted values for each group based upon those time points and the respective slopes and like all that jazz. What you got?
I don't know.
Did you run this yet?
Yeah, I ran
Yeah.
it. And that's what I got from running it.
Error assign. Oh, this is weird. This is an error that I've seen. First of all, yeah, it actually, I don't think it matters. It's this weird error about like, yeah, there, it's fine. It's an error that I've seen recently in some newer, like just very recently, but you can fix it just by restarting RStudio. First of all, you make me nervous without save this, man. Save this somewhere, that's fine.
Oh, I didn't even.
Save it, like put it in the wherever the data is. I don't know, I'll let you do that on your own. Ignore that error for right now, but you can fix it by closing your session and restarting your session. I've seen it occasionally before, but it's like some weird like stuff in memory not clearing out error. I'm not sure. But yeah, at some point save the code. You can put it anywhere you want. And you just hit the save button or Control S from your keyboard to do that. Okay, great. So now that we have the line data, we can plot the lines.
Can you download code?
What's up?
Can you like download it?
What do you mean? Like all the code that I put in the Slack channel, you could just download that and then just open it directly. Yeah. Yeah, totally. Yeah, don't leave all those untitled. Eventually you'll lose everything. Okay, great. So now we're going to go ahead and plot the lines. So to do that, I'm going to use the lines function. Why? Whenever you use the plot function, that creates a brand new plot. But we actually just want to draw on the plot that we already have. So I'm going to go ahead and use the lines function. And in the lines function, you can use the same syntax that we always use. We can say y as a function of something. So we're going to say as a function of t, where the data come from line data, right? And now we need if you think about this though, we're going to have two lines, and that's cool. But if I just run this right now, they're both going to be, oops. Okay, so here's a problem. There are a couple problems that we've noticed. First of all, the two lines that it drew, you can see both of them, but they're not the right colors, and it also like connected them together, which is not exactly what we want to do, right? We want to do each line separately, right? So the first thing I'm going to do is I'm going to do the following. I'm going to rerun, hold up, let me just, from my screen, rerun everything from the plot onward. Let's just make the line for group number 1, okay? So to do that, I'm going to use logical indexing. I'm going to say line data, but I'm only going to take the rows where dgno equals g11, okay? And that's going to draw one line. Wait, what? Hold on one second. Oh, my bad. This is D, it shouldn't be D. That's why. Great, so that's just one line. So why does that work? Again, okay, so let me, before you type anything, look at what I'm doing in the console first so that you understand what I'm doing. So I am doing line data, see what this does, line data $geno equals G11, comma, this keeps all the columns. Now it's the table, but it's just one group, okay? And then if I change this to be G22, it's the other group, okay? So that's what that's doing. So I'm going to draw each line separately. And you can imagine, have you ever done a for loop before? A for loop? A loop? No? Yeah. Oh, you have done a loop. A loop. Yeah, that's called a for loop usually. So for all of the values in the genotype, you can loop each one. We're going to do it manually now, but you can imagine you could write a for loop to do that. So in this case, these are both the lines. And now you have 2 lines on screen if you do both of those.
Can you split it?
Yeah.
Or is it the same error?
That's the same error. The only way to clear this error is, now that you saved it, oh, you saved it. You saved it. Hell yeah. Okay, so now you can just restart RStudio and that'll make it go away. Okay. If you don't like the error, if you don't mind, I don't think that doesn't do anything. But regardless, if you just copy and paste this line and just change it and add G22, then you'll get the other line too. Yeah, so I'll let you do that. Just ignore that error for now. Just don't worry about it. Because the only way to clear...
Do you mean just like closing it?
Yeah, you have to close the whole program and reopen.
That's what I've been doing the whole time and it's always...
Wait, what's up?
That's what I've been doing the whole time and it...
Wait,
Untitled's always been the same.
Well, it remembers the last things that are still in there that weren't saved. So maybe save these. Okay. Maybe some of that is coming from that. Don't worry about that error for now. Let's just let the error keep happening because that's not an error that's going to impact anything. But I think it has something to do with you not saving things and like closing things down and like reopening them and like something like that. Something like that. But I don't think it matters for anything. But yeah, just go ahead for now, leave it open in the interest of time, and go ahead and just copy that line to a second line and just change G11 to G22 and you'll get the other line. Okay, cool. And now, of course, obviously you can add the color. And what's nice about R is all of these functions have the same parameters. So I'm going to just go add another parameter, col equals blue, and col equals red. Okay. And in this case, I didn't rerun all the way from the plot. I just let it draw on top of it. It just drew a blue line and a red line on top of the other ones. Okay. The black line is actually still on there, just like underneath, and if you were to export it to certain file formats, it would actually know that. But for right now, this is all that matters. Great, so that's how you draw the lines. So now you got the lines, and you got the data points. Now if you want to draw that shading behind it, that's fun. This is a little more advanced, but I think it's just 2 of us, and we have the time, and we have a few minutes. We got a few minutes left here. We may as well learn how to draw that shading. The first thing we need is we need the standard error for the data points, right? So how do we find that? We find that the same way that, there are a couple different ways to do it. We find it the same way that we found the standard error the other day, which was by doing the math of multiplying like a transformation of the standard error of the coefficients. So you can use that same math to do that. In other words, if you were to take, this is not the way I'm going to teach you to do it, but I just want to show you the math how you do it, right? If you made, so here is, remember that if you make some sort of matrix W, this is how we found the standard errors for like the slopes and stuff like that. We had some matrix that extracted the slopes and we multiplied it by this variance covariance matrix, and that's how we get the standard errors. So if you said that W equals again, no type that I'm just showing you. If you use this model matrix function, which is basically t, what was it, Gino times t. What did we put in the model here? Hold up. It's a function of Gino times t. Okay. This matrix W has like the intercept and the Gino being either a 0 or a 1, and the t, and then the Gino times t or whatever, which is very similar to the same thing that you see in the actual model itself, right? So we can use that to calculate the standard errors, because if you do this and then you say SE equals W, standard VCOV model, this linear algebra stuff again, and then you get the square root of the diagonal of that. Those are the standard errors for all those data points, okay? But the easiest way to extract that, and I'm going to leave this in the code, so this is the, I'll leave this as the mathematical direct calculation of the standard errors, right? But instead of doing it that way, I'm going to go back up to where we created line data and we calculated the y values. I'm going to add in a little bit of code real quick. So we created this thing, okay? What we can do is we can have the predict function directly output the standard errors for us, okay? So to do that inside the predict function, I'm going to go ahead and say, I'm going to make this a different variable and we'll add it back into line data manually. I'm going to call it, let's call it predicted values. And we're going to say, leave everything in the predict function the same. So we get the model, the new data, and then we want to say, I think it's called SE fit equals true. And that is going to calculate those standard errors for us. Okay? And what it returns to us is this predicted values object here, and it has a couple different items in it. You can see it has the fitted values, and then it has the standard errors for each of the fitted values. I'm going to come around and just see that you have that real quick. Yeah, there you go. Yeah, there you go.
And run it?
Equals true. SE fit equals true. Yeah, yeah. The value of that parameter is true. All capital, you have to put it in all caps. True and false is all caps. Yeah, there you go. So this is saying, before you run it though, before you run it, this has to come after line data is created, right? So put it in that next line. Go up one.
Oh, wait.
You we're getting rid of 107. We're replacing it. Okay, okay, so check it out. You just said new data equals line data, but you haven't defined line data till later. So you need to define that first. That's why. So I'm going to move this down. And we're just going to scooch this. Where's your delete key? I'll just put it here. There. Okay, so you need to make sure this is defined before that. Great. And then, where's your home key? Man, I don't know how to use this computer.
Home key?
Yeah, where you go to the beginning of the line quickly.
I don't think I have that.
Oh, everybody has that somewhere. Oh yeah, it's home, it's here, you have to hit the function key to do it. So like if you're here and you hit this, watch this. I can quickly go to the end of the line or the beginning of the line.
Oh.
Yeah.
Never knew.
Yeah, kids don't know how to use computers these days. Okay, so we're gonna rewrite that line. Predicted values. Just go ahead and run those two lines right there. Okay. So now if you inspect predicted values from the console, you'll see that it has a couple different things in it, right? It has the fit itself, and then it has what it's calling the standard error of the fit. So you see both of those? Great. So now we're going to add those into line data. Now that we've calculated them, we're going to add them in. We're going to say line data y equals predicted values $, and it's called fit. That's the fit. And then line data standard error is the predicted values I think it's called SE fit. Yeah. Okay. So we're just extracting those. It was too hard to like do all of that in one line, so that's why I'm doing it this way. Okay. So now you have Y and SE. Okay. Let me see if you got that. Oh, you're good. You're good. You're good. Take your time. Yeah. But you see what I'm doing though, right? Okay. Yeah. So now if you inspect line data, and whenever I say inspect, I just mean type it in the console and just take a look at it. You'll see that you have the Y values and you have their standard errors in the command line. Okay, so that means at time 1 hour, if you're genotype number 1, the expected value is like 1.39 plus a standard error of 0.03. That's the uncertainty around that little estimate, that prediction, right? So that's the error in the model on that, okay? So now if we want to draw that shading now, this is fun. This is very fun. To do this, we're going to use, basically what we need to do is we're going to use the polygon function. And what that does is it basically, let me see if I can draw this real quick. We're going to use a function called the polygon function. And the polygon function is going to say, basically, if you have a list of numbers like 1, 2, 3, 4, 5, 6, 6, 5, 4, 3, 2, 1, and then you did, I don't know, 10, 20, blah, 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 blah. It's going to do this. It's going to draw this shape like this, whatever, then draw up, and then draw back over the opposite direction, and then connect and make a shaded object. Okay? Does that make sense? Yeah. Okay, cool. So we need to generate this thing where these values over here come from the line plus or minus the standard error. Okay? Hopefully that makes sense. And we're going to just like execute it, but then maybe if you spend some time now that you have saved the code, you can spend some time reviewing that. So I'm going to say line data. Let's call it, actually, yeah, that's fine. We'll call it line data lower is just the Y values, so line data Y minus line data standard error. And then line data upper is line data Y plus the line data standard error. Okay, I'll let you take a second and type that. But all this is doing is it's creating a new variable, either called lower or upper, and that's going to be the upper and lower boundaries of that shape that we're going to draw. Okay. So now when you do that, eventually you're going to have these two new columns. And basically we want to draw that shape to show shading between, in this case, 1.36 and 1.42, and so on and so forth. So let me know when you have that or if you have any issues. Yeah, there should be four columns. You have the fit, you got the standard error, and then you got the fit minus the standard error and the fit plus the standard error. So just look at that. Cool, so we want to draw the shape that basically, if you consider group 1, we're going to start this on the low end and then trace back around on the upper end and make a completed shape. So to do that, it's going to be fun because it's a syntax that's annoying, but it's fine. We're going to draw polygon. Great. We need to provide it x and y coordinates, okay? So x equals, what is the x coordinate? Well, we want to use time, right? So we are going to say line data t. This is ugly. Is there a way to do it nicer? Yeah, let's do it nicer this way. I'm going to do this in a couple lines because if I do it all in one line, it's going to be really ugly and you're going to complain. So we're going to do it in a couple instead. I'm going to say group 1 is line data where line data geno equals g11. I'm going to separate that out right now because that way it's easier for us to deal with. And then group 2 is line data geno equals g22. Because if I have to put all these logical tests and like all of that all in one thing, I would do that for myself normally. However, it's going to be very ugly. So I'm just I'm just chopping that table in half. I'm taking the stuff for group 1 and the stuff for group 2 and just separating them. So if I look at group 1, you can see that's just the data from group 1, and it should just be like 9 long or whatever. And then group 2 looks like that. So it's just I just took the table and just sliced it in half. Cool. Okay, great. So now that we've sliced it in half, it'll be easier to draw both of those boxes without you going crazy and wanting to kill me. So we're going to do polygon for group number 1 first. I'm going to put a little comment here that says group number 1 shading. Right? So polygon, we're going to put the x equals group 1 $t. Okay, because we're taking those are the x coordinates. But we're also going to do something fun. So before you type anything else, look at the command line. What I need for the polygon is I need to have a vector that goes 1, 2, 3, 4, 5, 6, but then goes 6, 5, 4, 3, 2, 1. Like has all the edges so I can trace around the whole thing. If I just take group 1 t, that looks like that. But then I also need, using this function, rev group 1 t. What the rev function does is it gets the other side. It traces back around the other way. Right? So I'm going to use the C function, which normally does a vector, to combine both things. If I do C group 1t and then rev group 1t, it'll make one long vector that's the whole thing that I want. Okay? Cool. So this is a little complex. You see what I mean? That if we had to do all that logical testing in that line at the same time, it would get really messy. So I'm just going to say C group 1t, rev group 1t. Okay? And then y, when you get there, is going to be the upper and the lower from group 1, right? So C, we're going to make one long vector. I'll show you what it looks like from the console. Group 1 group 1 lower, group 1 upper is going to be these numbers. And you can see how they wrap around. It like gets small and then gets large again, etc. Whoops, my bad. This needs to be rev group 1 upper. There we go. That way it sort of like wraps all the way around. Okay? So when I do this, so I'm going to say group 1 lower, rev group 1 upper, and then give it a color, in this case blue. Whoops. Blue. If I do this, there should be a shaded thing. Here, I'll get my mouse out of the way. I'm going to do it with group 2. To do that, I'm just going to copy this whole thing and just change group 1 to group 2 stuff. Oops, my bad. Group 2. Change all this to group 2. And then red. Whoops. Okay. Put my mouse out of the way. What's up? I just changed every group 1 to group 2 for the second one.
Okay.
Let me see real quick. Yeah, I just copied it, pasted it, and then just make sure, yeah, exactly. And just changed all the group 1s to group 2s, and then made the color red. Cool. And then just make the color red instead, and then close the end parentheses at the very end on both of those. You need a parenthesis at the end.
That's it?
There you go. And you need one here too. There you go. Cool. Now try running both of those.
What happened here?
What's up?
Well, like, why is there X's on it?
Why or what? Okay, well, let's see. Go up. Let's figure it out.
Okay.
It looks like they went away. It looks like you fixed it after you did those parentheses. Don't run all of that. Just do the polygons. Do it one by one. Did you run these parts? Yeah, you did. They're there. Yeah. Yeah, so go ahead and run 118, 119, 120. You have, may I? It's probably an extra parentheses or an extra comma or an extra sign. Okay, that's fine. Okay. Should be okay. Unexpected symbol. Is this, did you type a 1 instead of an L again? No. Let's see, it doesn't seem to be complaining. Yeah, there it is. Well, that should be okay.
No?
There you go.
Nothing wrong.
No, yeah, it's all good. Great, great, cool. So now that makes the shading, and you can see the shading's relatively tight around the thing. Cool. And then the reason why the lines are below that is because then you can draw the lines on top of that, right? So now I'm just going to delete, just bring those lines up. But I'm going to do one last thing because that line isn't going to show up very well on that shading unless I add this. I'm going to make the line thickness thicker so that it's more obvious. So I'm going to say LWD equals 2. That's going to draw the line in thicker on top of the box that we just shaded in. Hopefully that makes it a little bit more visible. And then I'm going to show you one other trick we could maybe do to do that. Yeah, it's a little hard to see. If you zoom in, you can't really see it. Okay, so the reason why you can't see it is because the color of the shading and the color of the line are identical, right? So since the line is in the shading, obviously you can't see it. So another way to deal with this, there are a couple ways to deal with this. You can make the background of the shading more transparent so that you can actually see the line on top of it, or you can make it a different color. So I'm going to take the approach of making it a slightly different red color. So I'm going to go here. Let me find something where I can find hex color picker. Yeah. If you just go to Google, just open a web browser, and type in hex color picker, you will get something that looks like this. Google apparently has a tool for this. I'm going to take this, and I'm going to find like a lighter blue that I want for the shading. And let's see, I don't know, like maybe like something, maybe like kind of like this color, something like that, whatever speaks to you. See where it says the hex thing? If you hit this little like copy button right here, that code #37BEF0, R will know to draw this color correctly based on that code. So I'm just gonna go ahead and copy that and go back to R, and I'm gonna replace the polygon color with that color. Okay, I'm gonna do the same thing. I'm gonna find a red color that I like that's like a little bit lighter or like just a little different, like maybe like this salmon color, and pick that and put that in for the shading for the other one, because now the two colors will like look in the same family but be like distinct enough. So now when I do this, now it should be visible, except for I'm going to go back and I'm going to actually rerun everything from plot, because we're drawing like on top of other things, on top of other things, on top of other things, and it's not going to show up. So I'm going to go all the way to the top here and rerun starting from plot. I think that should help. I think. Yeah, you can kind of see it now. If I zoom in, like you see how this like red color and this like the blue color stands out really nicely. Wait, what's up? What do you mean? You changed the color? Oh, no, I know what you mean. You changed the color in your script. That's because you need to redraw the whole plot from the beginning. So You did that here, but the problem is that you're trying to draw this thing over something that's already shaded in. So you need to go back and go back to like get rid of some of these extra lines here, but you have to start from scratch and like redo the whole thing from up here so that it draws a fresh plot that doesn't have like all this. Because every time you execute this command, it just draws on top of what you have there already. So you're not going to be able to like tell, basically. Okay, and now drew the lines. So it made both of them the same color. So you probably want to make, you know, polygon number 2 some different or something like that. Oh, maybe you did them differently. Hold up. Okay, hit the zoom button real quick. Okay, that's not bad. Wait, why is that group 2 that color? Oh, because you just picked another bluish color. You must have.
Oh.
You didn't pick a reddish color for group 2.
Oh yeah, no, I didn't.
That's why. That's fine. That doesn't make it. That's fine. So you picked 2 like kind of. You can see. You know how R like interprets that color you put in and kind of shows you what it's gonna look like. Yeah. For group 2, I chose something from the red family. You decided to be a little bit more creative and choose a different color, which is fine. But you can kind of see that red line on top of there and that blue line on top of there as well.
How come mine shows and yours doesn't?
Well, it's just because I'm so zoomed out that you can't tell. So if I zoom in right now, you can see it.
I mean, it's like on the script.
What's up?
Like you said, when I show the color, like it shows like a little like.
Oh, yeah, I think it's because I have a custom like background set to my scripts right now and like it's just not showing it. Whereas if I had left the default, it would. But anyway, if you look here, you can see the red line on top of this. Alternatively, I already have the color from the shading. I could just make the lines black at this point, right? Because I don't need that color on the line itself, you know what I mean? So like I could just do that instead, and I bet that would look a little bit nicer. Let's see. Yeah, now this looks ugly in the little tiny version, but if I zoom in, then you can see the black on top of those colors, right? So you could do it that way. You can experiment with it, you can have fun with it. I'm gonna go ahead and change this line thickness back to like just normal line thickness. But yeah, you can play around with all these parameters until it kind of gets to be the way that you want it to look. Like maybe like this is like reasonable. So this, I just like made the lines black and then left the shading that color. And like that's reasonable. I think that's reasonable. So this is the final product. These are the graphs. So you can tweak it to your heart's content. The very last thing, and then we'll stop. Make sure to save your code. Is I'm going to show you how to export this. For right now, I'm going to show you how to export this from. Actually, let's do it from the command line the correct way. So I'm going to go in here. No, let's do it this way first. We'll do it that way another time because it's just more complicated. From right here, if you click this export button right on the little plot window, after you're done plotting however you want, you can save. My favorite way to save is to save as a PDF, and I'll explain that why maybe in a future workshop. I'm going to save it as a PDF, and it's going to go in the same thing. I'm going to call it lorazepam graph.pdf, let's say, and just hit save. And then it should appear in my folder, and there it is. So, yeah, there's my graph. Wherever you set it in your original code at the top, remember you have that set WD function all the way at the top to put everything somewhere. So you probably put it somewhere. Let's see where you put it. Go all the way to the top. It's going into, okay, so this won't, wait, how did you even? You don't even have a folder called that, so how did you?
Oh, I just copied and pasted from your last one.
I know, but, oh, I see. Oh, so you just opened it, right. So you downloaded and opened it. So we need to put this somewhere that makes sense for you, okay?
I'm really one of the other ones I have it.
Yeah, you're good. I'm just gonna put it in documents for now. And let's go ahead and, you probably had some errors because you were trying to save things and it's like going into a folder that doesn't exist on your computer. Which is fine.
I think I have a folder somewhere that I put it.
It's all good. The problem is, what I'm curious about is how you even loaded the data, though, because, like, that's supposed to be in that folder. Wait, do you have it? Is it in doc? Where's the data at?
I don't know.
Oh my God, Christian. So, one rule of coding is to, like, know where the data. Oh, it's in there. Okay, so you got it in the documents folder. So that should work just fine. Oops, what's this dot doing here? What's this all about? Here, I'm going to simplify your life.
Is that not needed?
No, that was from all the stuff we were doing last week. That's, I mean, you could leave it, but that was just me showing, like, illustrating how to calculate all that stuff by hand, so that you would have a better understanding of all that. But that's okay. Go in. I don't know, a line got deleted, but it's okay. We don't really need that right now. Okay, cool. There. Okay, that's a mistake. Oh yeah. If you wanted to do it that way. This, by the way, was just to demonstrate to you. Got a lot of mistakes here. Oh, battery's on. Oh, it's all good. We'll be done here in a second. This is just to demonstrate to you. This is just the math way to calculate the standard error that the predict function above is doing automatically. So if you needed a little bit of a deeper understanding of how to calculate the thing that we're doing right there.
That just showed up?
What?
That symbol that just showed up.
Oh, I don't know. I think I hit the function key instead of the...
What is that?
I don't know what that is. That's your computer, man. Okay, so...
The only time I've seen is when I do caps lock, like...
Okay. Well, anyway. Okay, so that should now have this graph in there. Razapam. And there it is. Cool. Sweet. Great. So you can mess with those colors. You can mess with all those things. By the way, you can see how that polygon, your computer's getting low, but you see how this polygon has this like black border all around it? You can get rid of that if you look at the last thought I'll leave you on, your computer's about to die, but is like any function, like if you hit question mark polygon, because you just don't remember how to do something, inside the RStudio window it'll show you like what all the options are, and like I can put border, I can do all sorts of things, and like
Null mean?
what's up?
Null.
In this case, null means you don't want to have a border, right? So in that case, if you set it that way, then you would tell it to get rid of the border. But there are lots of things that you can do. Oh, I'm sorry. It looks like if you want to set border equals NA, then you get rid of the borders. There are lots of different ways to do this. There are lots of different options you can set inside these things, right? So in this case, if I just added this option here, border equals NA. You read the documentation, you can see, you can see what all you can see what all you can do to change the appearance of your plots. In this case, I just got rid of that little black border, save as PDF, lorazepam graph.pdf plot. And then, you can tweak that and tweak the appearance of your final output. So this is what my final one looks like. Looks like that. Yeah, and that's...
What do you like? Why do you make these?
Why do I make a plot?
Yeah, like what do you make them for?
Well, you might be trying to show someone what the results are, right? So you might want to put it into a manuscript for a paper that you're going to publish. You might want to sometimes visualizing data is the best way to like see what's going on. So sometimes I make plots just for myself, just to kind of explore the data a little bit and kind of get a better sense of what I'm doing or what the results are. Sometimes it's hard to see when everything's just in a table, right? And then for publication purposes, the same reason. Those visualizations are useful for someone who's reading something to get a sense of like what's happening. In this case, you see this negative slope in both of the groups, that there is this decay of drug over time, blah, 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 and that there's a little bit of a change in one group versus the other. You can now observe that sort of visually in the plot. So yeah, there are lots of reasons why you might make a plot. But yeah.
And do you get your own data when you make them?
Of course, yeah. Yeah, normally I'm not just using plots from the literature. Normally it's from like my own work, right? right? So if you have data that makes sense to make as a graph like this of any kind from stuff that you do with Megan over the summer, you can mess around with that. Lots of different ways to edit these plots and do different sorts of things. Okay, cool. All right, thank you. Yeah, totally.
I don't really think I'll ever. Cause I have 3 weeks left. Around.
You should make a plot before you leave, like one of your data of anything. You probably have something, right? Nothing?